Hi, I'm Hashir. I'm a senior at the National University of Singapore studying computer engineering. I am the current team lead for Bumblebee Autonomous Systems and I help to develop software to aid in sensor optimization for this year's RoboSub.
Hi, I'm Sean. I'm a senior at NUS studying computer science, and I work on computer vision in Bumblebee's software team.
Hi, I'm Yongjae from Bumblebee. I'm a senior studying electrical engineering at NUS. I'm working on the acoustic subsystem of the vehicle.
Hi, my name is Karthikeyan. I'm a year 2 computer engineer and I'm working on sensors.
BBAUV 4.0 features highly sophisticated sensors that are optimized to deliver the best possible performance. We have designed our hull and the placement of our sensors for maximum accessibility during testing and debugging, and have ensured that their performances are not affected by other components. Our vision system relies on sonar camera sensor fusion, which increases the reliability of our measurements, while the hydrophones are used for both the pinger task as well as for inter-vehicular communication.
Our main hull was designed with sensor placement and optimization in mind. It features an internal aluminum compartment that separates the electrically noisy components such as the ESCs from the sensors like the IMU and acoustic systems. This allows sensitive components to be protected from any electrical noise from the inductive loads through grounding isolation. This also ensures that our sensors are working with optimum functionality and are able to work adequately so that we can achieve our competition objectives. Our sensors are also mounted such that debugging is as effective as possible. PBAV 4.0 sensor connections, such as those of the cameras, DVL, and IMU, are placed at the lid for easy accessibility, therefore reducing the time needed for debugging. This ensures that our pool tests are conducted with efficiency, which is crucial during the lockdown period where access to the pool is limited.
We plan to deploy both our BBAUV 3.99 and our BBAUV 4.0 to complete the competition tasks. To facilitate this dual vehicle strategy, an inter-vehicle communication system is required. However, each AUV also requires its own pinger localization system to attempt the pinger tasks. As such, we have integrated both the pinger localization and the inter-vehicle communication functionalities into one unified hydrophone hardware. This is made possible by the dual transmit and receive capabilities of our hydrophones. This ensures that both functionalities are utilized fully while conserving space as additional sensors and boards are not required, allowing us to reduce the size of our AUV to gain more points during the competition.
Our sensor system adopts a multi-sensory approach for tracking and localizing objects of interest by fusing the data obtained from the camera and front-looking sonar. The sonar is used to identify the range and azimuth to the identified objects, while the elevation is determined by forward projecting the search space and matching detections from the sonar to the front camera. Such an approach produces reliable measurements, which gives us a high confidence rating for the buoy and torpedo tasks. To support continuous development of the AUV during the COVID-19 pandemic, a simulator was developed based on the UUV Simulator, a package that contains gazebo plugins and ROS nodes for simulating physics and sensors of autonomous underwater vehicles. The simulation allows the sensors to be quickly tested in a virtual environment for logical and architectural issues, speeding up processes by tightening the feedback loop between writing and testing code, in turn decreasing turnover times for more agile software development. We have also added task obstacles to the simulator this year, which allows us to prototype our task-specific logic quickly and effectively for our mission planner.
Due to the COVID-19 restrictions, most of the testing for acoustics modem was done in a tank in our lab. Basic functionality was tested initially via loopback testing, and in-water performance was tested in the tank. By testing different frequencies, we managed to select the carrier frequency that achieves the maximum range. Following that, a compromise between the data rate, error checking, and packet loss is found via testing. However, as we are testing in a tank rather than in a pool, the multipath effect faced by the modem is significantly higher. In order to mitigate the overlap between the pings, we opted to include gap intervals to ensure that signal received from the previous message and current data do not overlap. Due to the low transmission sensitivity, the signal at the receiver is low relative to the noise. In order to ensure a high enough signal-to-noise ratio for a successful demodulation, we decided to include an additional bandpass filter in the receiving channel.